Unit 6.5, interpreting the behavior of accumulation functions involving area. The key thing here is to remember the fundamental theorem for most of these problems, okay? If we understand the fundamental theorem, we're in good shape, but we also need to combine this with everything else that we know in order to answer these questions. So the first thing is just understanding an accumulation function, this first problem that we have in front of us. So we want to find out which of the following values is the greatest, where they give you g of x and they define it as the accumulation function of f, where here is f. And let's go through each one of these here. So let's look at a to start. So is g of negative 3 the largest? Well, what is g of negative 3? G of negative 3 is equal to the integral from negative 2 to negative 3 of f of t dt. Now, if you look, here's negative 3, here's negative 2, right? This integral from here to here is going to be negative because you're integrating backwards, which means that your integral is negative, or that this is equal to, if we flip this the more comprehensive way, this is equal from negative 3 to negative 2, but then negative, right? Using our that we could swap the bounds of integration. And this area is above the x-axis as a whole, so then that means that this part will be positive. The integral will be positive. This part here without the minus is going to all be positive, right? From negative 3 to 2, that's a positive area above the x-axis, right? So that's going to be positive, and then the whole thing's going to be negative. So this value is less than 0. So that already, is less than 0 as a whole. So, okay, so this is less than 0. Okay, now let's look at negative 2. Well, negative 2 is already greater than that because the integral, what is g of negative 2? G of negative 2, again, just understanding our accumulation function, negative 2 to negative 2 of f of t dt. Well, we should know that the integral from a to a is always 0, and that's already greater than a, so we know it's not this one. This one equals 0. Now let's see, g of 0. Let's understand g of 0. Let's see what we got here. So g of 0 is going to be from negative 2 to 0, and that's exactly whatever area this is right here. I have no idea. Okay, so that's positive, it's greater than 0 for sure, which is all fine and dandy. Now, well, I don't know, now I could put greater than 0 for C, and then let's look at g of 1 now. So let's see if I can contrast this with g of 1. Well, g of 1 is from the integral from negative 2 to 1 of f of t dt, of course. And what does that look like? Well, from negative 2 to 1 is all this area right here. And that's for sure greater than that orange area, right? So this entire green area is the orange area is only part of this green area. So this is for sure the largest one right now. So this is, let's say, greater than C. Right, and C is the largest. C is greater than 0, is all we know, and this is greater than C. Now g of 2, here's 2 over here. This region here is gonna be a negative, right? It's gonna subtract from the overall value of the integral, right? So this part here is gonna subtract from this green part here, right? You're gonna be adding, and then it's gonna be negative. So the whole thing for g of 2 would be the sum of this blue part that I'm shading that blue part, right, the area there, and then minus whatever area is here, which is going to wind up being less than the green part. So it is for sure choice D in this case. This is the correct answer. And you should just understand how the accumulation function works. Fairly straightforward, only a good understanding of the accumulation function is necessary in that case. But in this case, now we need to know a little bit more. We need to know, I think, the fundamental theorem. Absolutely. In this case, you need to know the fundamental theorem. So let's see how to do this. Let's read this. The figure above shows the graph of f. If f of x is equal to the integral from 2 to x of g of t dt, which of the following could be the graph of y equals g of x? Okay, so now let's see. Well, I don't know much. I don't know. Sounds weird. I mean, maybe I use the fundamental theorem. The fundamental theorem, right? This here is a function defined by an integral. And if we have this here, right, what do I know? Well, I'll know that the derivative of f prime of x is equal to g of x, right? Because I have it where I just plugged in that x for t. And with that, right, I want to find the graph of g of x. So really, I just want to find the graph of f prime of x. And I'm given a graph of f. So if this is a graph of f, what does its derivative look like? Well, the derivative represents the slope of the tangent line. And for this line, what is the slope of that tangent line? Well, it's always positive. That's first of all, is this slope positive? Is the slope going up? Yes. So f prime of x, or g of x, right? It's equal to g of x, is always positive. It's always greater than 0. That's one thing. Then the next thing is that is the slope of this line changing? Is the slope of the tangent line of any of these points, is it changing? No, it's constant. So g of x, or f prime of x, equals some constant, which means that it's a horizontal line. And the thing that satisfies both of these conditions is just choice A in this case. The key here was to see that you needed to use the fundamental theorem on this to know that f prime of x was equal to g of x. Now the last one. Okay, now this last one, really good test of whether we understand everything that's happening here when it comes to accumulation functions. It's really rooted in testing the idea, so put this aside. Don't worry about this problem. Let me give you a refresher. So we'll read this problem after, but let's first understand something else. Let's remember that if I'm in a car and I'm going, I don't know, 60 miles per hour, right? We should remember that my change in position, right? So here's t, here's v of t, right? I should remember that if I want to find out how much I've changed in position from time A to time B, right? And I don't know, maybe my velocity is fluctuating, right? A great deal, right? Then if I wanted to find out my change in position, I would just integrate this function from A to B. And you could see it in a more concrete example if, let's say, I had it clear. It wasn't, it wasn't just a general function. Let's say I said, let's say I wanted to find out how far I traveled. If I were going, I don't know, 50 miles per hour, right? 50 miles per hour. And then A, right, this is time, 3 hours, and then let's say, I don't know, 7 hours, right? So that's 4 hours, right? So I'm going 50 miles per hour for 4 hours. So what's my change in position? So remember that this represents the change in position, delta S, or delta X, let's say, for simplicity's sake. This represents the delta X, because this is its X position at time t. So this is delta X, the change in position. Make sure you realize that it's change in position. This is 4 hours, right? 4 hours, 50 miles, 200 miles is my change in position. Okay. Now, with this reminder, let's attempt to read and try and do this problem here. An object traveling in a straight line has position x of t. So its x position is given by x of t at time t, okay? if the initial position, so it gives you initial position, okay, x sub 0 equals 2, and the velocity of the object is given by this function. What is the position of the object at time 3? So what are they looking for? They're looking for x of 3. That's what they're looking for. Okay, that's a first good way to start this problem, to write what is it that they're looking for? X of 3. And now you want to remember that, and this is something strange, right? The change in its position between x of 3 and x and its initial position, right? Change in position. Let's write it out. Change in position, just to be very clear. Change in position, okay, is whatever it is at x sub 3 minus whatever its initial position is. That's how much it changed its position. But we should also remember that here, what was the change in position for this? It's the integral from whatever bounds from 0 to 3, right? In this case, it's from time 0 to time 3, right? Is going to be the change in position. Again, like, for what was my change in position here? From the 3rd hour to the 7th hour, the integral, this area, right, from 0 to 3 though in this case, because it took the role, A took the role of 0, B took the role of 3, right, and then this would be 3, and then I would have changed position of 150 miles, right. In this example here, to relate it back, is the integral of the velocity function. So the velocity function is the cube root of 1 plus t squared dt. And now what I can do is I can now solve for the missing variable, the missing piece, not variable, the missing piece, which is this x3 here, because I equate these two things. And I know that x sub 0 is 2, so that's just minus 2. X sub 3 equals, and now for this part, and this is key, this use calculator. So you gotta get out your calculators in this case. Use the calculator for this definite integral. And what you'll get for this definite integral is you'll get 4.512. And then, if you want to solve for what its position is, x sub 3, you add 2 on both sides. And you get that x sub 3 is going to be 6.512. And then that is choice D. Okay? Take your time with this. Go through this one. Relate the concept of change in position is, of course, whatever its position is at one time minus what its position was at the other time, and that's how much it changed in position between those two times. Okay, so I'm looking for the position at x of 3, right? Well, if I can compute how much it changed in its position from its initial position, then I can compute where it is at x sub 3, right? If I'm at, if like the drone, we were talking about drones, so if I know how high a drone is originally, and then I know that it changed its altitude by 100 feet, well, then I know I can find out what its position is at the later time after it changes its position, which is x sub 3 in this case. Okay, and I need to remember that the change in position is the integral of the rate of change, right? The change of accumulation, right, is the integral of the rate of change, right? If it's a drone and it's moving altitude, you want to find out how much altitude has changed, the change in altitude, then you can just integrate from one time period to the next time period. And it's just like in this simple car example, right? What's the change in position in this case where A is 0 and B is 3? Well, the change in position is 150 miles. What its original position might have been, right? Maybe that's a little bit more tricky, but from the time 0 to time 3, it changed its position 150 miles. And in this case, you're given that the original position is 2. So you know what that original position is, and then you could sit here and you could compute what its change in position is between the two. So then the only thing that's missing is what its final position was, which is what it's asking. And seeing that you want to make this relation very difficult, you have to do this over and over. You have to really get familiar with this idea.